Now let's consider another thin film example. So let's consider a soap bubble. And y'all have all seen soap bubbles. Okay. And so what happens is that light reflects off of the soap bubble, but it reflects off a different place in the soap bubble, and it has this iridescent sort of quality to it. And what's happening is you're getting maximum reflection, but the soap bubble is non-uniform. It's thick and thin in places, and so sometimes you're getting reflection with one wavelength and sometimes a different wavelength of light. And so let's figure out what's the range of thicknesses here for a soap bubble to give reflections in the visual part of the spectrum. Okay. So we want to maximize in the visual part of the spectrum. So if you remember the visual light, so the wavelength for visual light ranges between 700 nanometers and about 400 nanometers. 400 nanometers being the shortest that you can really see. That's near the boundary between violet and ultraviolet, and 700 nanometers being close to the boundary between red and infrared. The exact wavelengths you see are in part genetic, but on a human average is somewhere in the neighborhood of 400 to 700 nanometers. Now, index of refraction inside a soap bubble, air, so it's 1. Outside the soap bubble is 1. So in the soap bubble, it's a little bit more than so it's about 1.35, roughly that of water. Okay. So I want to know the range of thicknesses. Now we want to have maximum reflection. Okay. So in this case, because the index of refraction on the inside is less than the index of refraction of the bubble, we have several things happening. So when we reflect off of the outer surface, we have a phase change. But if we reflect off the lower surface, there's no phase change. So maximum reflection now, because now the phases do not match. So the phases do not match. Now, as we said when we derived our expressions for thin films, if the phases don't match, we get constructive interference. If 2L equals m plus 1/2 lambda naught over n. Okay. So this is going to be our constructive interference, so that is going to be the maximum reflection. Now remember, this is exactly opposite if the phases do match. If the phases do match, then that equation would give us the destructive interference, and so the minimum reflection. So you have to really watch out for whether or not the phases match. Okay, so I want to know the range of thickness. So L is going to be m plus 1/2 of lambda naught over 2n. Okay. So the minimum thickness, that's going to be m equals 0. So L equals lambda naught over 4n. Okay. Now, we already said the n was 1.35. Okay. So 4n is going to be 5.4. So this would be lambda naught over 5.4. So L lambda naught over 5.4. So the range of wavelengths, okay, so if lambda naught is 400 nanometers, that's the shortest you can see, then L is going to be 400 over 5.4. And so that's going to be 74.1 nanometers. For lambda naught equals 700 nanometers, then that comes out to be 129.6 nanometers, or we can just round all these things to 100, round that to 130 nanometers. Okay, so that means your soap bubble here can range from, so L, in order to get this iridescence in which you have total reflection, or not total, we have maximum reflection rather, for visual light, then L has to be anywhere between those two ranges, 74 nanometers and 130 nanometers. And so that's the range of thicknesses that would give you that. Now, if the thickness is more than that or less than that, then you don't get that color reflected. But this is for m equals 1. We could also do it for, or rather, m equals 0. We could have done it for m equals 1, or we could have done it for m equals 2. So those are other that would give you other possible ranges. And I leave that to you to look at how that works. So these are examples here for thin film interference. This is a third example of 3. This would be for a soap bubble in which the index refraction on the inside is less than the index refraction material. The previous 2 examples, we had a gradient index refraction least on the outside, greater in the material, and greatest in the substrate on which the material was placed. So these examples, and so now we could do more with this chapter 35 and talk about the intensities at different levels and so forth, but that's just getting a little bit beyond where we need to be with the coronavirus shortened semester.